welcome to Playing with Mathematics. Today I am going to discuss the three problems in the continuity or discontinuity. It is a very important part of the calculus. Now, problem number 1, fx equals limit n tends to infinity, limit t tends to 0, sin square factorial n pi x divided by sin square factorial n pi x plus t square. Now, here case 1, suppose x be a rational number. Then factorial n into x, factorial in x. Rational number means x is of the form p by q, where pq are integers prime to each other, pq prime to each other, and q not equals 0. As n tends to infinity, we choose factorial nx into an integer. Suppose x equals something 2 by 500, suppose this. So we can choose n greater than equals q such that q that is factorial n into p by q 2 by 500. If we choose n greater than equal to q, suppose n equal to 500, so 500 factorial by 500 into 2, this is equals an integer. So factorial nx is an integer in this case. Therefore sin square factorial n x into pi must be a 0. Integral multiple of pi, so it is 0. And hence fx in this case, when x is rational, fx equals limit t tends to 0. This is 0 by 0 plus t square, and this is equal to 0. Case 2, when x is an irrational number, then factorial n x not an integer. This is not an integer. So sin square factorial n x into pi must be square, so it must be less than 1 and greater than 0. Therefore we can write fx equals limit n tends to infinity, limit t tends to 0, 1 by 1 plus t square by sin square factorial n pi x, and taking limit t tends to 0, and this is the bounded, it is not equals 0, so the limit of this function is 1. So we get fx equals, fx equals 0 when x is a rational number, and this is equal to 1 if x is a irrational number, which is another problem, which is discontinuous for all real x. So problem for real x, so the problem 1 is solved. Now the second problem is similar to the problem 1. Here we divide into two parts. One is belongs to Z, another is not belongs to Z. Here case 1, when x is an integer, that is x belongs to Z, then sin square pi x is an integer. Suppose x equals m, therefore sin square m pi, this is also 0, and in this case fx equals limit n tends to infinity 1 by 1 plus n into 0, that is equal to 1. And case 2, when x is not an integer, x is not an integer. In this case x is not an integer. In this case sin square pi x, what's the value of sin square pi x? It is never attain the value. Sin square pi x always less than 0 and greater than 0 and less than equal to 1. It can be 1 if x equals half, not belongs to Z, then this is equals 0, this is equals 1, so it can attain 1, but it can never attain the value 0, because x is an irrational number. Suppose pi x is pi root 3 or pi root something, so it can never be a integer part. Pi x is not an integer or does not belong to Z, therefore it can never 0. So sin square pi x lies between this and this. In this case fx equals limit n tends to infinity 1 by 1 plus n, and is as a function lies between this and this. Suppose this is equal to m in m, therefore this is equals 1 by 1 plus n tends to infinity, this is equal to 0. So fx equal to 1 when x belongs to Z, and this is equal to 0 when x does not belongs to Z. So this shows that fx is discontinuous for all Z, because Z plus, suppose x equals 3, therefore limit x tends to 3 plus or minus, x equals 3 plus or minus, fx must be 0, and at the point x equal to 3, f of 3, this is equals 1, f of 3 equals 1, but limit x tends to 3 plus or 3 minus, left and right hand limit of fx is equals 0. So it is discontinuous for all. This is discontinuous for all Z. Now the third problem, fx and gx is continuous for all x belongs to R, then hx equals limit n tends to infinity fx plus x to the power 2n into gx by 1 plus x to the power 2n. It is continuous everywhere except x equals plus minus 1, and find the condition for hx is continuous this. Now for the case 1, in this case 1, fx hx equals limit n tends to infinity fx plus x to the power 2n gx by 1 plus x to the power n. In this case x square, if x square less than 1, case 1 x square less than 1, in this case this is equal to 0, so this 0 and this 0, so therefore hx n tends to infinity, hx equals, that means hx equals fx. Case 2, when x equals, case 2, second case, x equals x square equals 1, that means x equals plus minus 1. In this case, x to the power 2n equals 1, so hx equals fx plus gx by 1 plus 1, that is equal to 2, or f1 plus g1 by 2. Now for the third case, case 3, now we divide x to the power 2n in the numerator and denominator. Fx hx equals limit n tends to infinity fx by x to the power 2n plus gx divided by 1 by x to the power 2n plus 1. So this is equals 0, so this is equals 0 and this is equals 0. Therefore in the third case hx equal to gx. So we can write fx equals hx equals fx when x square less than 1 and fx plus gx by 2 when x equals plus minus 1, and this is equals gx when x square greater than 1. So at x equal to plus 1 and minus 1, x equals plus 1 and minus 1, this is discontinuous. Suppose at x equals 1, left hand limit h of 1 minus, that means f of 1, and right hand limit h of 1 plus, this is equals g of 1. So also h of 1 equals f1 plus g1 by 2. So we say at x equal to 1 hx is not continuous. To find the condition if it may be continuous, then this equals this equals this. If we set f1 equals g1, then left hand limit f1, right hand limit is also f1, and g1 is also f1. Therefore h1 equals f1. So hx is continuous at x equal to 1. The condition is f of 1 equals g1. Similarly, if h of f of minus 1, if we set f of minus 1 equals g of minus 1, then hx is also continuous at x equal to minus 1. In this case, f is continuous everywhere. Otherwise, it is discontinuous at x equal to plus minus 1. Thanks for watching. Stay healthy and stay safe.